Hello again. In this video we're going to talk about rotational inertia. Now rotational inertia is just the rotational equivalent of mass, but it's not just mass, it's where the mass is placed. For instance, if we look at, say, a merry-go-round, like the playground merry-go-round, the kind you have to spin, and say there was a child on a merry-go-round in position 1. He had a 10 kilogram mass, and he's 2 meters from the center. It's a pretty big merry-go-round, I know. But say we calculated his rotational inertia here. At position 1, it's just I equals mr squared. So his 10 kilogram mass times his 2 meter radius squared gives us 40 kilograms meter squared. Doesn't really mean much right now. Keep that in mind. Say the kid moves outward towards the outer edge of the merry-go-round, and now he's 3 meters from the center. Well, what's his new rotational inertia? Notice his mass did not change. He's still 10 kilogram mass. However, his radius has changed, which will change his rotational inertia. So now we have 10 times the 3 meter radius squared, which gives us 90 kilograms meter squared. So we notice an increase in rotational inertia as he moved outward. And that makes sense because if we look at the formula, if you increase your radius, that will increase your rotational inertia. But let me ask you a question. What is that going to do to the speed of the merry-go-round spinning? In other words, will it cause it to increase, will it cause it to decrease, or will it not have an effect at all? In order to think of that, think of a figure skater spinning. And when she pulls her arms and legs in, she spins faster. But when she extends them, she slows her spin down. That same principle is being in effect here. So with these two things in mind, and if I gave you another piece of information saying that the merry-go-round is initially spinning at 50 RPM, that's 50 revolutions per minute. It's a little less than 1 per second. So it's also spinning pretty fast. This kid will be puking in no time. So we're going to go to what's called the conservation of angular momentum. That is your I1 omega 1 equals I2 omega 2. The I1 and the I2 we just calculated here. Think of the 1 and 2 as before and after some change. The change was the kid moving from the first position to the second position. That changed, that physical change of him moving caused a change in a lot of things. In the rotational inertia, which also had a direct effect on the rotational velocity. Omega 1, I'm giving you as 50 RPM. We're solving for omega 2. In other words, the speed after the change. 1 is before the change, goes traveling 50 RPMs. After the change, that's what we're going to find out. So I1, which is 40 kilograms meter squared, times omega 1, which is your 50 RPM, is equal to I2, which is 90 kilograms meter squared, times omega 2. So in this case, we're solving for omega 2. To get omega 2 by itself, it's being multiplied by that 90 kilograms meter squared, divided by 90 kilograms meter squared. What you do to one side of the equation, you must do to the other. So basically these cancel out, and you're just left with omega 2. The kilograms meter squared cancel out, so you're just left with RPMs. And 40 times 50 divided by 90 gives us 22.22 revs per minute. So it's slowed down from 50 revs per minute to 22 and change revs per minute. That's because the kid moved outward toward the outer edge. In general, I want you to think of a specific relationship here. That relationship is between two different formulas. The two formulas we just used for that example. One for rotational inertia, which is I equals mr squared. And the one for the conservation of angular momentum. That is the I1 omega 1 equals I2 omega 2. Now, typically what's going to change is the radius. If the radius increases, naturally, that's going to cause an increase in the rotational inertia. That's a direct relationship there. But that increase in radius, like we had here, caused a decrease in rotational velocity. When you apply it to the conservation of angular momentum, it's an inverse relationship. So again, if the kid moves outward or if the figure skater extends her arms out, then that's going to overall indirectly cause the spin to slow down. However, if the kid moved inward or the figure skater pulls her arms and legs in, that's a decrease in the radius. That decrease in radius directly causes a decrease in rotational inertia. Conversely, that decrease in rotational inertia will cause an increase in rotational velocity. She pulls her arms in, she's decreasing her rotational inertia by decreasing her radius, but that causes an increase in her spin. So she actually speeds up. So that is the relationship between these two formulas. And it's very imperative that you get those two. One last thing, using the same merry-go-round. If we had two different students or children on the merry-go-round, say we had child 1 and child 2, and I asked you two questions. First off, which of these two has a greater rotational velocity? Secondly, which of these two have a greater linear velocity? Well, the first question, which has a greater rotational velocity, they actually have the same rotational velocity. They'll be making the same amount of revolutions per unit of time. Think of it as you're on a carousel, like a Kennywood, where you're on one horse, your friend's on the horse right next to you. The whole time you're spinning around, your friend is directly to your left. They're not making any more revolutions than you are in any unit of time. So rotationally, they're traveling with the same speed. But linearly, the person closer to the outer edge is traveling linearly faster, because kid 1, that's their path. Kid 2, that's their path. They're making the same amount of revolutions per unit of time. However, if we stretch kid 1's path out linearly, that's what it would look like. If we stretch out kid's 2 path linearly, it would look like that. They're traveling those distances linearly in the same amount of time. So linearly, the kid in position 2 is traveling faster. That's why, for instance, in horse racing or car racing, you want to get to the rail, get to the inside. You're traveling a shorter distance than if you're going to the outside. These are just a couple things to keep in mind as you continue through Module 8.